Hi. This is a supplement to week 3 of the Executive Black Belt class on Introduction to Statistical Inference. Very often we don't have the time to cover this in class, so here's a supplemental lecture for it. This is really meant to be a gentle introduction to two of the absolutely important and most important steps in branching what I would say is true modeling and true statistics from what everybody thinks of as statistics. Most people think of statistics as calculations from data. I'm calculating something like the mean, I'm calculating something like the standard deviation. To the statistician, to the mathematician, to the data modeler, to the person who really wants to use statistics, and that's you, you really want to think about the larger picture, and you want to be able to say, when can I say that a small data set or a representative sample means something in a larger sense about the entire population? That's really what I care about, right? I don't really care about that particular sample. I really care about the population. So we're going to take our first steps into the techniques of that. The two techniques that are used, the two key techniques are, one is hypothesis tests and one is called confidence intervals. And they both kind of go together. One is great for telling you what's not true, and one is great for telling you what is true. And that's why they go great together. It's like, what was it, peanut butter and chocolate in the old commercials. Okay, peanut butter and chocolate. Okay. All right. So basically, there's two things, two objectives that we want to come out with this. We don't want to know what all the tests are, but we want to understand why we'd want to use a confidence interval. And we want to basically see what are the basic mechanics of what they look like and how they act. Okay? So we're going to do one example. We'll do it both in Minitab and Excel statistics to get you comfortable in it. No matter which one you're most comfortable with, you'll be able to do it. Both do it fine for what we're going to be doing here. Okay? All right. So what we're really talking about in statistical inference is, I know that say this strange object right here that I've got drawn represents my population. When I sample from that population, what I'm really doing is I'm getting these little dots, right? I'm sampling different people, and if I've sampled in a way that is representative, and I've tried to show this by saying I've kind of spread out my samples throughout that population, I get numbers. And those numbers are given as the following. I can calculate things from. I can calculate something called the mean, right? And that's this guy right there, X bar. We often call the mean. I'm going to try and from now on call that the sample mean. Or I might be able to calculate S, which is the standard deviation. Or actually, it's an estimate of the standard deviation. And here I've got X50, which is the median. Okay? X50 just means it's the 50th percentile. And here I've got P, which is a proportion. I can say proportion good, proportion bad. Remember the whole discussion about capability. Capability is a proportion, a special one that says proportion good or proportion bad. But we could think of it as whenever I have attribute data, or whenever I have discrete data or category data, I can think of the proportion of coin flips that come up heads. That's a proportion too. Or the proportion of patients at a hospital that are male. That's a proportion. So P stands for proportion. Or it's okay to think of it as percent. That's okay. Well, in any event, when we're bridging, what inference does is it bridges that gap between the sample and the population, and it says, okay, when can I say that this particular X bar is representative of the entire mean, which I've given as sort of the Greek letters, mu in this case. Mu would be the mean. Sigma is used for standard deviation. That's a sigma right there. I'm using nu for the median. That's the Greek letter nu. And, of course, you recognize pi, the Greek letter pi, for proportion. That's just the symbols that I use, but mu and sigma are pretty universal. And what we really want to do is know when we can make that generalization to say this particular mean represents the population mean pretty well. That's what we're trying to do. So hypothesis tests and confidence intervals allow us to make statements about the population using those using sample statistics. We never will actually know these guys over here, or we probably won't unless we can sample the entire population. We probably will never know these, but we can know these by sampling. And so the trick is really to say, how do we know when we've sampled enough so that we can say we know this? That's it. Okay? It's a tough thing philosophically to get down, but once you get it, it's like riding a bike. You'll never forget it. Okay, so let's just do an example. And really what we're talking about here is, can I believe what I see? So in this case, I've given a box plot, and this is an example that we're going to go through. And one of the reasons I've given you this in our examples to look at the PGA wheel. I don't know if you remember that, but remember when we're analyzing, we always look at that PGA wheel. It has nothing to do with golf and everything to do with analysis. That's an A, fellas. Okay, and I make my Y here. And remember, we start out with the practical, and that happens to do with like a wonder statement, like in English language, I wonder if gender is a driver of gas mileage. Then G stands for graphical, which means I make a plot, and that's why I'm right here. Okay? So suppose I'm confronted with a plot or even a table of numbers, and the real question is, how can I believe that what I think I see in this plot is real? So for example, it certainly looks like the mean here, I don't know if that's exactly the mean, but the mean is somewhere in that box, is greater than the mean here. In other words, do women really get better gas mileage than men in their driving? That would be the question that's going on in my brain right here when I look at this plot. Can I believe what I see? In the plot, inferential statistics is the A part, analytical, that's going to tell us, yes, I can believe what I see. Or no, I can't. Okay. And that's really the question. How likely are the differences? A statistician would say it this way: how likely are the differences I'm seeing due to chance alone? That's what a statistician would say. I like the more vernacular. Can I believe what I'm seeing in either a plot or a table? All right. So a hypothesis test gives us the answer to this question. Let's walk it through. Now, the key point in this section really is that if we sample for any two populations, whatever it is, men and women, day shift versus night shift, hospital A versus hospital B, middle market segment versus large market segment, we're always going to get a different answer, always. It's going to differ. The question is that difference significant or not, statistically significant or not? And we define statistically significant as very unlikely due to chance sampling. Okay? How do we determine that? We run a hypothesis test. That's the answer. So, and the reason why they go together in a great way is that hypothesis tests are saying either yes or no. Yes, it's true that they're not the same. But it doesn't tell me how different they are. A confidence interval actually tells me how different they are. Let's do an example, and we'll see. Here's just a process that we can go through, but I think the PGA process makes some sense too. Again, I like plotting the data first, writing out a real-world question, translating to math, carrying out the hypothesis, translate it back. That's all very well and good, but that if you remember the PGA wheel, the PGA wheel, PGA, is really doing all of those things. Start out with a practical, say what I'm trying to prove, go to a graphical, make a picture of it, and then run the analytical. That's our hypothesis test right here. That's this guy right here. Right? And then translate it back into real-world language. That's this right here. That's getting back to the practical, which we always want to end up at. Okay, we're going to work through this example using gas mileage. And so let me do that. Okay, so if I do that, I've got the file open, gasmileage.xls, which you should be able to obtain. You should have in your data directory. And what I'm going to do is, I see I've failed to do this. I want to also open up Excel statistics. There it goes. So now we're going to open this up. All righty. There's my gas mileage. There's Excel statistics. So you'll notice in this case we've got, let me draw the box. In here we've got gas mileage as our key output. And our key input here is gender. And gas mileage is a number. And gender is a cat. All right? So far so good. And there's our process, whatever that process is, a bunch of process steps. Okay, so practical, graphical, analytical. Okay. P, I wonder if gender is a driver of gas mileage. Let's make a plot. If it looks like it is, then let's do some analysis, nail it down, and make a conclusion. Sound good? That's what we're going to do. Okay, so we've got one num, one cat. Excellent. So it looks like we can make a number of different, we can look at some sample statistics, but I like making a plot first. Nothing obvious from this guy, but if we go to the summaries tab, there usually is some interesting information. If we look at percentage-wise, it certainly looks like, looking at this plot right here, it certainly looks like women, which is F, females, get higher gas mileage on average than men are getting. Looks like that's true. We can also look at it on separate frequency charts. Boy, it really looks true here, doesn't it? There's women, there's men. Boy, it looks like there sure is a difference in the mean. And those are just two different ways. We can also look at a box plot. It's not my favorite in this one, but change the scale. Again, it certainly looks like women are getting more gas mileage on average than men are. So we can run the hypothesis test. Now let me show you what that looks like. The hypothesis test is going to look a little bit different. What we're going to do in a hypothesis test, and it's a little bit interesting, is a hypothesis test, we'll get used to this, we break it up into two different possible states that are true. What we call the null and the alternative. And we can think of this as the null as, there's no difference. No difference. In this case, in means. But we can also test things like standard deviations. That'll come later. Let's test the means first. And this one would be, there is a difference in the means. So mathematically, the way of writing that is to say our mean for women, UF, why did I write mu5? UF, let's try that again. MUF minus MUM is equal to 0, right? If there's no difference, if I subtract the two, I should get 0. On the other hand, if there is a difference, I would write MUF minus MUM is not equal to 0. So, again, that's not much of a bold statement. It either is or it isn't. So I'm breaking up the world in two possible things. And this one I call the null. And this one I call the alternative. Some people call it the alternate. I call it the alternative. So this is the null hypothesis. This is the alternative hypothesis. And basically we look at the data and we say, well, from the data, which one do we conclude is true? Okay? All right. So the way that it works is we assume that the null is true. It's like in the courts we do innocent until proven guilty. We assume that the null is true, and if we find out that the probability it's true or the likelihood is very, very small, we will reject the null and go with the alternative. It's that simple, okay? So we can actually do that in Excel statistics. We'll do lots of other examples with this. In Excel statistics, that's actually given right here. If you go to Tests by 2 Categories page, oh, look at this. See, it's already The nice thing about Excel statistics is a lot of stuff is already given to us. Here's our hypothesis test. mu1 minus mu2 is equal to 0 versus it's not. And it says the p-value is 1.05 times 10 to the minus 11. That's 1 with 11 zeros in front of it. So 0.0000, whoops, no, I didn't want that. I wanted this. Point 0, oh, come on, 0.000000, 1, 2, 3, 4, 5, 6, 7, got a few more, 0.000105. That's a pretty small number. And we can think of that as, I know my statistician friends are going to be rolling over in their graves, or if they're living, they're just rolling their eyes. But this is kind of like equal to the probability. I know they don't like it when I say this, but it's a good way of thinking of it. The probability that H0 is true. Okay? Which is a pretty darn small number. So that's going to tell us essentially that instead of going with H0, we're going to go with HA. And there really is a difference. There really is a difference. Mu F is not equal to mu M, and the difference is real. It's statistically significant. So it's saying that what we saw in that plot, or those plots, is real. Okay? Now the confidence interval gives me actually the interval for what we think is the difference. And it says that, in this case, it's a 95% interval. That 95% interval is somewhere between 3.9, I'm going to round this off, between friends, that's 3.9, and 2.8. So essentially, women are getting from somewhere between 3.9 and 2.8 miles per gallon better than men in this particular set of data for the cars, whatever it was. But keep in mind, this is fictitious data. As much as I would perhaps want to say it's not, it is fictitious data. But again, this would say that there is a real difference, and notice how that the confidence interval, by the way, the actual difference is minus 3.34. The best estimate is minus 3.34, or almost 3.5 miles per gallon difference, but there's a plus or minus that's added to it, and that's where we get the interval. Okay? It's like a margin of error. It's like adding a margin of error in a poll. You know, somebody might say a particular candidate is getting 52% of the vote plus or minus 3% margin of error. That's what we're talking about. The confidence interval tells us sort of the likely values of the true difference in this case. Okay? So that's it. That's how you do it in Excel statistics. And if we go back to our gas mileage, yeah, I don't need that update. If I go back to our gas mileage page, and this, yeah, I'm going to get rid of that again. And remember, we had the practical, the graphical, the analytical, and here it was. I wonder if GM and gender. I wonder if gender drives gas mileage. Here is, it certainly looks like it's true, looks true. Remember, we did the histograms, and for the men it looked like this, and for the women it looked like this, something like that. That was the picture that we got. We did the analytical, and you bet we said we can believe the plot. It is true. It is true. And in a practical sense, we'd go back and we would do something about it. Now, if we were trying to improve a process, we might say, well, let's go out and get all the men trained to not waste so much gas mileage and stuff like that. Basically, that's it. That's how it all works. And once you get used to looking at the p-value and choosing a test, this all becomes very, very simple. Make a plot, see if it's actually true what we see, and if it is, move on. If it isn't, move on. If it is, formulate a solution based on that. If it isn't, look elsewhere. It really is that simple. let me show you how to do the test in Minitab. Also pretty straightforward. Hardest part in Minitab, you got to get the data in there. But you'll also notice in Minitab we will have to learn that this was a statistical test that we did. See, Minitab can do box plots too. Here's Minitab's box plots. Mileage versus gender. Okay, see that? Looks pretty good. Looks pretty good. Let's do a t-test, or let's do the test. In this case, we've got what's called a two-sample t. As we go on throughout the class, we'll note that this is when we're testing means, we use t-tests, and this is one of them. We've got samples in we've got samples in two different columns. The first is mileage. The second is wait a second. We have samples in one column. Our sample is in mileage. Our subscripts or our labels are in gender. And go ahead and click Okie dokie, and there we are. And there's our p-value, which is again, is very, very small. It doesn't show it going to the 11 zeros, but you'll notice that we got the same confidence interval and the same estimate for the difference. Okay? So again, in both cases, Minitab would say, and Excel Stats would say, no, we're rejecting this. We assumed it was innocent, no difference, but that we're rejecting that in favor of the alternative. There is a difference, and that just means that the difference is statistically significant. Okay. So hopefully, and by the way, all of this is simply given in the book as well as our, our null and alternative hypothesis and the Minitab results. Okay? Okay. So before we wrap up, I want to just kind of summarize what we've looked at and some of the key things in statistical inference. The key thing is we're moving from statistical inference means bridging the gap between sample and population. And we do that by running a hypothesis test, one or more hypothesis tests, and we get confidence intervals along for the ride. They come along with it. I'm a confidence interval person more than I am a hypothesis test, but I have no choice. I got to go through a hypothesis test in order to get the confidence interval. And just one I guess, last comment on this is that hypotheses are great at telling you what's not true, what's not true, or what something isn't, and confidence intervals are great at saying what is. What is. Okay, so so that's it. We'll cover hypothesis testing and statistical inference more throughout the rest of this course, but this is just the beginning. It bridges the gap between sample and population. If you can do that, you will raise your game tremendously, and you will set yourself apart from all the folks who simply can calculate means and standard deviations and don't really have a good way of making decisions between them. Okay, so hope you enjoyed this, and I hope you found it illuminating, and we'll see you next time.